Hello and welcome to the video. Today we're going to go through another differential equations episode, and today we're going to go through exact equations. But the first thing we need to do is understand what our basic format is for an exact equation. So the basic format is m dx plus n dy equals to 0, where m and n are some functions of x and y. But the first thing we need to do is to actually test if it is indeed exact, and to do that we need to take partial derivatives. So if we do partial m over partial y is equal to partial n over partial x. And if this holds true, then it is in fact an exact equation. So the first step we want to do is do this for ours to make sure we have an exact equation. So if we want to know how do we know which one is m and n, you just look at our basic format. The dx goes with m, the n goes with the dy. So we have a dy here, so this is our n, and then this will be our m, because that's where our dx is. So we need to check if it's exact. So we need to take the partial derivative with respect to y for the m. So we need to take the derivative of this with respect to y, so treating all the x's as constants, and just take the derivative with respect to y. So which would give us a 6xy, because this will go away, and then when 2 comes down, we just have 6xy. And then we want to know if this is equal to the partial derivative of n with respect to x. So we need to treat everything as a constant except for x. So all the y's are constant, so this whole term will just go away. And then for this one, we are left with a 6xy. And since they are indeed equal, we do have an exact equation. So now what we can do is we can proceed to find the integral of each of these terms, because we want to find our generic function. So m is denoted as partial f over partial x, and then n is denoted as partial f over partial y. So we want to take their respective integrals. So for m, we want to integrate with respect to x, and for n, we want to integrate with respect to y, and that'll give us our function f. So if I were to take the integral of the m, what I need to do is I will separate it all out. So we have a 3xy squared dx plus the integral of sine of x dx. And then we need to do, for our n, we will have plus the integral of a 3x squared y, and then now it's dy. And then we have plus the integral. I'm going to pull a 1/2 out of the bottom here, so I'm going to pull that out to the front. Then we'll have a 1 over y squared plus 1 dy is equal to the integral of 0. So now that we have all of our stuff separated out, we can take their individual integrals, starting with the first one with respect to x. So we will have an x squared, and the y squared will stay, and then we have a 3. But remember, if we were to take the derivative of this to get here, we need to add a 1/2 so that the 2's will cancel. So this is over 2, and then that's our first one. And now we have the derivative of sine of x with respect to x, which is just cosine of x. But we have to remember it's negative, because the derivative of cosine of x is a negative sine of x, but we have a positive, so therefore we need a negative, so negative and negative will cancel. Then for our next one, we are with respect to y. So let's do this one. We now have a y squared x squared 3, but remember, if we take the derivative, the 2 will come down, so we need to get rid of that, so because we don't have it here, so we need to add a 1/2. And then for this last one, we have 1/2, and then this is just the integral arc tangent or inverse tangent of y, and then this will be equal to some function c. But what we need to do is figure out which terms stay and which ones do not. So for any terms that have more than one variable in it, they need to match. So if you notice when we did, if I split it here, because that's where we had, if we split it, we have our m and our n, and when we did this, we have an x and y here, we have an x and y here. They match, so therefore we take that and keep it. So you have a 3/2 x squared y squared, and you only need a once because it's in each one. And then anything with respect to x, there's nothing on the other side. That's good. We need to take that. So we have a cosine of x, and then this one we just have a y, which is good. So we just need to take that one as well. And then this will be equal to c. And then that will be our answer to this exact equation. And if you're not sure why I took like this one but didn't take that one, and then I took this one and I took this one, the idea is if you have one variable, so if I have just an x, it needs to show up on one of the sides, whichever one it is. So since we did the integral here, it showed up here, it's not on the other side, that's good. We just need the one because it has one variable, so it gets included. Same for this. It's only on the one side because it has one variable, so it gets included. For this one, it has two different variables, so it needs to show up on both sides. So I have one here, they match, it's great, so then we can include that as well. And then that's our generic function. So for this next example, we want to do the same thing. We need to first remember that we need to check and see if it is indeed exact. So to do so, we need partial m over partial y is equal to partial n over partial x. And so we need to take the derivative of the m with respect to y, but we don't know which one that is. So m is always going with our dx, because we have m dx plus n dy equals 0. That's always our format for the exact equations. So since we have a dx here, this will be our m, and then we have a dy, so this will be our n. So we take the partial derivative with respect to y in this case. So the derivative of the tangent of x, there's no y, so it goes away, gets treated as a constant. And then this one will have a 2y. And then we want to know if this is equal to the derivative of this section with respect to x. So if I take the derivative with respect to x here, I just get a 2y, and then the cosine of y goes away because there are no x's involved, and therefore they are equal. So we have an exact equation. Knowing that we have an exact equation, we can now proceed with integrals, because we need to find that the partial derivative of f with respect to x is equal to m, and then partial derivative of f over the partial derivative of y is equal to n, because the goal is to find some function denoted as f, so we need to take our perspective integrals of each one. So to do so, I want to take the integral with respect to x of m, so it's a good thing we have a dx there. So I'm going to take the integral of tangent of x dx plus the integral of y squared dx, and then for our n term, I want to take the integral with respect to y. So I need to do a 2xy integral of dy plus the integral of cosine of y dy. That'll be equal to 0. So if I take the integral of tangent of x, I will get natural log of secant of x. And if you're not sure how I got this, I made a video just breaking down the process of getting how from tangent of x to natural log of secant of x, so be sure to check that out if you're not sure how to get to this point. And then for our y squared, with respect to x, we will just have an x y squared. And then for this one, we need to take the integral with respect to y. So I will have a y squared, and the x will stay because it's constant. And then if we take the derivative of this, the 2 will come down, we'll subtract powers, which is in fact good. So we just leave it as this. And then for this one, it just becomes sine of y, and that is it. And so now what we need to do is figure out our function f. So for this one, we only have one variable, which is great, so we need to include that. So we have natural log of secant of x. And then we will have, this one has two variables, so it needs to show up on both sides, which it does, so they match, so it gets included once, because we don't want to include it more than once, because we'd just be repeating it. And then we have one variable here, which is great, it shows up on one side, so it gets included, sine of y, and then this will be equal to some unknown variable c, and then that will be our general solution to this problem.